Have you ever looked up at the night sky and felt a sense of wonder? A feeling that you are part of something vast, something ancient, something mysterious. Out there in the silent darkness between the stars lie secrets we are only just beginning to understand. One of the greatest of these secrets is a question that has puzzled scientists and dreamers for decades. It is a question that touches the very limits of our knowledge, the very fabric of reality itself. What is on the other side of a black hole? The answer, if we can find it, might not be what you expect at all. It might change everything we thought we knew about our universe and our place within it. This is a question that can feel like it belongs in a science fiction movie, but black holes are not just fiction, they are real. So, what exactly is a black hole? In the simplest terms, it is a place where gravity has become incredibly, unimaginably strong. Think of it this way: Earth, a much denser neutron star, and finally, a black hole. Everything that has mass has gravity. You have gravity. The Earth has gravity. The Sun has gravity. But what if you could take a massive star, a star many times bigger than our own Sun, and squeeze it down into a space no bigger than a city? All of that mass, all of that gravity, would be concentrated into a tiny, dense point. The force of gravity there would become so powerful that nothing could escape its pull. This is how many black holes are born. The famous boundary of a black hole is called the event horizon, not a surface you can touch, but an invisible border, a one-way door into the unknown. From far away, a spaceship seems to slow, dim, and redden, freezing at the edge before fading. Inside, the traveler feels nothing crossing, but once past, all paths lead inward. Once you are inside the event horizon, where do you go? According to general relativity, all the matter that falls into a black hole continues its journey to one single place. It is pulled toward the very center. All of that material is crushed down into a point of zero size and infinite density, a singularity. Imagine taking a mountain, a planet, a star, and crushing it smaller than a grain of sand. The singularity is the ultimate end of that process. It is a place where space and time, as we know them, cease to exist. The pull is infinitely strong. Our equations break down, like dividing by zero. Fascinating and terrifying. Not a passage, but a final destination. Matter is stretched and torn by incredible tides, nicknamed spaghettification, drawn into a thin stream of atoms and added to the dense center. There is no other side, no new universe, just the end of matter, space, and time. Yet many physicists distrust infinities. They signal incomplete theory. We likely need quantum gravity to replace the singularity with something else, perhaps even more bizarre. If the singularity is not the final answer, what else could be inside a black hole? Some wondered if a black hole might be a gateway, one end of a tunnel through space-time, a wormhole, an Einstein-Rosen bridge. Imagine two dots on paper. The long path crosses the page. Fold the paper, bring the dots together, and poke a tunnel between them. A shortcut. A wormhole, in theory, bends four-dimensional space-time, creating a shortcut. Falling into a black hole could be like entering that tunnel. The journey might lead to an exit, perhaps even a white hole. The opposite of a black hole. Things only come out, never go in. You might emerge in a distant galaxy in a fraction of the time, or at a different time altogether. But models show wormholes are incredibly unstable, likely collapsing as anything passes through, unless held open by exotic matter with negative energy or negative mass. The black holes we observe look messy and turbulent, not smooth tunnels to other worlds. Most physicists believe astrophysical black holes are not stable gateways. Whether the inside holds a singularity or a wormhole, there is a deeper puzzle, the black hole information paradox. In physics, information is the unique, detailed description of every particle, the blueprint that makes a star and a spaceship a spaceship. A basic rule says information can never be truly destroyed. It can be scrambled, rearranged, or hidden, but not lost. Imagine, you burn a book. The words seem gone, but the information is transformed, encoded in the smoke, the ash, the heat, and the light. In principle, gather every particle and you could reconstruct the book. The universe keeps a record. Here is the paradox. Throw the book into a black hole, and from the outside it disappears. If it hits a singularity, it is crushed. In a wormhole picture, it exits elsewhere, lost to us. Black holes seem to delete information, but physics says information cannot be deleted. Something is wrong in our understanding. Many of the world's greatest minds believe solving this paradox will lead us to a deeper theory. The paradox is not just a brain teaser. It is a crucial clue, a message from the universe that there is more to discover about reality itself. And then came a stunning twist. In the 1970s, the brilliant physicist Stephen Hawking made a stunning discovery. He tried to combine gravity with quantum mechanics. He found black holes are not completely black. Strange quantum effects at the horizon make them leak energy. This faint glow is called Hawking radiation. Empty space is a bubbling sea of virtual particle pairs that pop into existence and annihilate. At the edge of a black hole, one can fall in while the other escapes, making it look as if the black hole spat out a particle. The escaping particle carries energy away, so the black hole loses a tiny bit of mass. The process is incredibly slow, but over unimaginable timescales, a black hole can shrink. Eventually, it can evaporate entirely in a final puff of energy. If black holes evaporate, where does the information go? Perhaps it is encoded in the Hawking radiation itself, carried away in subtle correlations. As scientists wrestled with the singularity and the information paradox, an even more radical idea emerged. What if, at extreme density, matter does not end, it bounces? Some quantum gravity theories suggest the collapse rebounds, expanding into a brand new baby universe. Called black hole cosmology or fecund universes, it paints a cosmic tree of offspring. Each massive star collapsing to a black hole could plant a seed for a new universe, hidden beyond the horizon. That universe would have its own Big Bang, its own expansion, perhaps slightly different laws. Our universe might descend from a parent cosmos. Universes good at making black holes would have more offspring. This could explain our Big Bang as part of an eternal cycle of birth, life, rebirth. Of course, highly speculative, with no way to test. Yet it stems from attempts to merge gravity and quantum mechanics. Where did our universe come from? Are we alone? What is the fate of everything? The black hole may be a gateway to understanding creation itself. Let us return to our brave traveler, the one who crossed the event horizon. What would they actually see and feel? It depends on the black hole's size. In a small, stellar mass black hole, tidal forces are extreme. Feet pulled harder than the head, stretching into a noodle of atoms before the center. In a supermassive black hole, horizons are vast and edge tides gentle. Our traveler could cross without noticing. For a time, they could survive inside, watching the outside universe speed up and distort into a small, bright window. Forward lies no point of light. The singularity, if it exists, is not a place in space. It is a moment in the traveler's future. No matter the thrust or direction, all paths in space-time lead to that final moment. There is no escape, no turning back. Our strange ideas, wormholes, escaping information, baby universes, seek a loophole in the sentence of cosmic doom. We explore them because a place where reality breaks down and everything is lost is something our science says should not happen. The traveler's fate forces us to build a better, more complete description of the universe. So, after our long journey of the mind, what is on the other side of a black hole? The most honest answer, we do not know for sure. We have our maps. Some lead to singularities, others to tunnels, others to reflections where information paints the horizon. The holographic principle suggests the inside is hidden, but the information about what fell in is stored on the event horizon, like a ghostly hologram. We are detectives solving a locked room mystery with only outside clues, lensing light, tugged stars, the faint whisper of hawking radiation over eons. Think of a sealed letter. You know a message is inside, but you cannot open it without destroying it. The paradox says the message cannot be lost. So how can we read it? Scientists are learning how to read the horizon, to decode nature's cleverness. Black holes are not cosmic vacuum cleaners. They are puzzles the universe gives us. Solving them may require a revolution, uniting the very large with the very small. And so, one final, open question. If we could one day read that unread message from the edge of a black hole, what would it tell us about ourselves?